have the great pleasure of introducing Dr. Cushing, who is an environmental epidemiologist and professor in the Department of Environmental Health Sciences at UCLA. And she uses epidemiology, GIS, and community engagement methods to evaluate environmental and climate-related exposures and health consequences, and with a particular emphasis on environmental justice, particularly with relationship to air pollution, hazardous sites, urban green space, heat islands, oil and gas. Well, there's so many things here: oil and gas drilling, drinking water quality, and sea level rise. So basically everything that, you know, will affect us in our current climate crisis. So Laura's going to talk about water, I think, today, right? Super exciting. So I'm going to turn it over to you. Thank you.
Thanks so much, Tracy, and for everyone for tuning in. Let me go ahead and share my screen. I was involved very early on in the genesis of the EaRTH Center before moving to UCLA. So it's great to see all the success, and I've tuned into a few of these webinars, even though I'm not officially affiliated. So I'm happy to share today some of our work on environmental justice and the human right to water in California. And I plan to speak for about 45 minutes. Is that good, Alana, Tracy, and then save some time for discussion?
Perfect. Oh, yes, excellent.
Okay. All right. So California, it was actually the first state in the country to legislatively recognize universal access to safe, clean, and affordable and accessible water as a human right. And that was a little over 10 years ago. But nonetheless, there are still roughly 1 million people in the state that are receiving drinking water that doesn't meet at least one regulatory health or safety standard. And even more are do not receive their drinking water from a water system, but rather rely on a private or domestic well, which is beyond the purview of the Safe Drinking Water Act, and for which we really don't have a good grasp on what types of drinking water quality threats those households experience. And so, you know, you may have heard in the news about well failures, people losing access to water from their domestic wells as a result of the drought and groundwater pumping by agriculture. So this is a quote from East Porterville is one of the communities that was very much affected by this. And this quote from the Porterville Reporter saying that in the most prosperous state of the richest nation in the globe, there are still towns with third world problems where obtaining drinking water is an everyday adventure. So that's kind of on the domestic well side, some challenges, but also among people who are served by a water system, we still really have almost two-tiered levels of access, with many communities, often on the fringe of cities in unincorporated towns, being left out of or not having access to safe drinking water, in part because they are not connected to neighboring larger cities. So this sort of selective annexation of bordering communities has resulted in inequalities in access to drinking water quality. So an example of this would be Matheny Tract, which is a small farm worker community, about 1,500 people in the southern San Joaquin Valley. It was founded originally by African Americans emigrating during the Dust Bowl. And, you know, encountering Jim Crow style racism such that they could only settle on the outskirts of towns and cultivated farmlands. Now the community is predominantly Latino and served by a water system with 2 wells that are both in violation of the arsenic regulatory standard, the maximum contaminant level, and have been since 2010. And the neighboring city of Tulare refused to extend its pipes to Matheny, even after the state provided $5 million in funding to do so. And so the state had to issue its first ever mandatory consolidation order to get the city to comply using new powers from a piece of legislation signed in 2015. So these are the types of challenges that we sought to address through this collaboration called the Water Equity Science Shop, which is a project of the UC Berkeley Superfund Research Program, led by Rachel Morello-Frosch, myself at UCLA, and collaborators at the Community Water Center, which is a nonprofit organization focused on water justice that works closely with communities in the Central Valley and Salinas Valleys on community organizing, education, policy advocacy, and they were really instrumental in getting the human right to water legislation passed. So our goals are to conduct community-driven research and policy engagement with the purpose of advancing water justice in California and reducing exposure to hazardous substances. So I'm going to share about two projects. The first has to do with inequities in drinking water quality, with a real focus on domestic well communities, since they were sort of a gap in our knowledge around this, because they are beyond the purview of drinking water regulation. So our goals were first to come up with a method to sort of systematically and comprehensively identify where communities are that are relying on domestic wells in the state, and to estimate groundwater quality in those areas. And two, to assess whether communities of color were at higher risk of poor drinking water quality, both in water systems and in domestic well communities, and to make that information publicly accessible in ways that could inform the implementation of policy, such as groundwater sustainability plans that were being developed under the Safe Groundwater Management Act, and efforts under the Human Right to Water. So to identify where domestic well communities are, this is a schematic that kind of illustrates the approach that we took. We started with census geography, census block groups, excluded census blocks that had no resident population from those boundaries. We had service area boundaries for community water systems. These are systems that serve more than 15 year-round residents. And so those were, we assume basically if anybody lived within the service areas of a community water system, that's where they got their drinking water. So we omitted those. We then obtained permits for over 900,000 domestic drinking water wells that have been drilled since the 1920s. And these data included the approximate location of the well within a 1 by 1 mile area, which are these square sections you see on the this map here. So we excluded sections that had no record of a well ever being drilled there. And then we took some additional steps to further refine these geographic locations by excluding places that did not have either tax parcels that were classified as residential buildings, or if none of those were present, building footprints, remotely sensed building footprints that we obtained from a national data set of kind of satellite derived estimates of where buildings are. And those last two steps we did because particularly in rural areas, which is where most domestic well communities are, block groups can be really big. So this is like an example from near Bakersfield, where this is a block group with about 100 people living in it, but they really all live, you know, right here on this this little end of the block. So to better characterize where people were really living, that's where those tax parcels and building footprints really helped us to zoom in on, you know, where these communities are located. We then estimated the demographics of these areas, starting with data from the American Community Survey, and assigning it to these building footprints and residential parcels, using a population weighted, and then using those to derive population weighted averages for each community water system service area and each domestic well area that we mapped, of these different measures here: racial ethnic composition, poverty rates, linguistic isolation, and housing tenure. We then took the step of trying to estimate water quality in these communities. So we looked at we focused on 3 contaminants because of their acute and chronic health risks. Also because of data availability. These are some of the most ubiquitous contaminants statewide. And for community water systems, they have to test for these regularly under the Safe Drinking Water Act. So we obtained those test results for the most recent 9-year compliance cycle. For domestic well areas, we relied on groundwater samples that are part of the Groundwater Ambient Monitoring Assessment Program, or GAMA program, run by the state. The maximum contaminant level is listed here for these 3 contaminants. So we averaged over the 9-year compliance cycle, using a time-weighted averaging for community water systems, try to represent delivered water quality on average for each system, averaging across their various sources of drinking water, so that we could compare across systems that may have different monitoring schedules. And then for domestic well areas, the time weighting averaging helped us with data sparsity, since there aren't that many samples. So next, these are the results. These show the mean drinking water concentrations across community water systems and domestic well areas in the state. We've split up the community water systems here by size: small, medium, and large, with small having less than 200 service connections and large having more than 10,000. So you could see that, if you look at the bottom line, a higher proportion of the population was estimated to receive average drinking water concentrations greater than the MCL regulatory standard for more than 1%. And smaller community water systems also had a higher proportion with drinking water quality problems than the medium. We also saw that communities of color faced higher risks of chemical concentration greater than half the MCL. We looked at half the MCL because MCLs are set with economic and feasibility considerations that are not necessarily health protective. So that's why we chose that benchmark. We also considered the public health goal, but it was below the level of detection for many of these contaminants. So, or some of these contaminants, so could not be reliably measured. So what I'm showing you here is prevalence ratios and 95% confidence intervals from general additive models estimating the association between contaminant concentrations and sociodemographic characteristics. Domestic well areas were modeled separately from community water systems. And so prevalence ratios above 1, so above the black line, indicated elevated risk. So for example, this square right here, this green square on the left, you would interpret as for every 10%, all of the predictor variables are scaled by 10%. So for every 10% increase in the proportion of the population that identifies as Latinx, the risk of having groundwater with elevated nitrate concentrations increased by about 20%. So you see similar elevated risks associated with the proportion of Latinx residents for the other contaminants, and then also for other people of color had elevated risks, but they weren't always as consistent with statistically significant. And these models controlled for the proportion of people that were renters as an indicator of socioeconomic status, region, and spatial autocorrelation. And the community water system models also included control for system size and the primary water source, groundwater versus surface water. As I said, one of our goals was also to make this data accessible. So Community Water Center developed this drinking water tool to help share this information. It has two, did I put the URL? Oh yeah, the URL's in the title there, so you can check it out if you'd like. It has two kind of doors where you can enter on the left, put in your address, find out who your water provider is, and find out information about your drinking water quality. And on the right, you can access kind of statewide data intended more for researchers or regulatory agency staff. And the tool development was really led by Community Water Center, who convened an advisory committee and hosted many stakeholder meetings to get feedback from potential users, including water justice groups, agency representatives, academics, and it's available in English and Spanish. Okay, so here's an example of the drinking water tool. If you go through that right-hand portal to access statewide data, you're looking here at Los Angeles community water systems, and you can see you can visualize average contaminant concentrations for 4 different chemicals here on the left: arsenic, nitrates, hexavalent chromium, and 1,2,3-trichloropropane. And then here's an example outside near Fresno. So this is looking more at the domestic well community. So on the left, you could see the number of people that we estimated to be reliant on a domestic well. How many in the middle, how many of those wells are likely to run dry under different drought scenarios that you can toggle between different scenarios. And then on the right, nitrate concentrations in the groundwater that are serving these from which these domestic wells are drawing. And we have the other 3 contaminants as well for the domestic well areas. And this tool, we did some, so if you're interested in reading more about this, you can see these 2 publications here. And we did Claire Pace, Amanda Fensel, and Lauren Boehner conducted some qualitative assessment of sort of the impact of this tool, doing interviews with people that were involved with this development and that used it subsequently. And from that, we learned that the data were used to help ensure that domestic well communities were better accounted for in groundwater management plans. And we also learned that the process of the tools development had an impact. So it increased communication between agency and community groups. It accelerated parallel efforts, including ones by the state, to map domestic well communities and assess drinking water quality challenges. And that, because CWC owned the tool, we found that communities trusted it more, whereas agencies were a little bit more hesitant to adopt the tool directly and instead chose to kind of take similar methods, but slightly different approaches in their own efforts to identify high priority areas in the state. We're now adding some things to the drinking water tool. So we're further refining the domestic well community locations using tax parcel data to better approximate where these wells are. And we have gotten some boundaries for some additional state small water systems, which are systems that serve between 5 and 15 service connections. And then we're adding information on several different types of drinking water quality threats, including PFAS detections and sources, pesticide applications focusing on pesticides that have been detected in groundwater or considered groundwater threats due to their ability to move through the soil, industrial cleanup sites, concentrated animal feeding operations in dairies, and oil and gas wells. And we are preparing to undertake some targeted and non-targeted analysis of tap water samples in high priority areas as identified through this work. So let me move now to the second project, which has to do with drinking water threats from oil and gas development. So most people, when they think of Los Angeles, they think of beautiful beaches and Hollywood and movie stars. But of course, the city was really founded or really grew as a result of oil. So Los Angeles Basin once produced a fifth of the entire world's oil supply. It now produces about 14 million barrels of oil per year. This photo on the right, upper photo is of the Huntington Beach. So you can see the oil derricks in the 30s, the oil derricks along the beach there. Today, about 500,000 people live within half a mile of an active oil or gas well in Los Angeles County. And studies have shown evidence of elevated air pollution near those drilling sites, higher metal exposures among residents living nearby, and lower lung function among people living near oil wells who are disproportionately Black and brown. By the end of the LA oil boom in the 1930s, LA had grown to be one of the country's fifth largest city and also one of the most racially segregated. So Daniel Cumming, in a great paper entitled Black Gold, White Power, Mapping Oil Real Estate and Racial Segregation in the LA Basin, looks at how federal redlining basically reserved the benefits of oil production for a white middle class while depositing its burden on communities of color. And so redlining refers to the denial of financial services to residents of neighborhoods that were deemed quote unquote risky on the basis of discriminatory criteria, including race. And so that's shown here on the maps on the left are maps published by the Homeowners Loan Corporation, which is one of several federal housing agencies that were established in the wake of the Great Depression under the New Deal to try to prevent foreclosures, stabilize the housing markets by making mortgages with longer repayment timelines available. So they kind of infamously undertook this national effort to appraise the investment worth of neighborhoods and publish these color-coded maps of perceived lending risks, assigning grades from A being the best place to make a loan to D being quote unquote hazardous. And the D areas were colored red on the maps, and that's why it's called redlining. So this practice institutionalized these segregationist policies and sentiments of the housing industry at the time that really valued the house of valued a house dependent on who lived in it, right? So neighborhoods that had racially restrictive covenants received better grades, and the result was that lenders channeled credit towards white neighborhoods with these restrictive covenants. So if you look at the notes accompanying the maps, and these maps have been digitized by the Mapping Inequality Project at the University of Richmond and are now being used by a lot of folks as a result of that. So if you look at the notes that accompany the maps, it's clear that the appraisers considered oil development as a detriment to property values in LA, but only when combined with the presence of people of color. So for example, this neighborhood I've circled here is Wilmington. This is low and middle income, primarily Latinx neighborhood in Los Angeles. It hosts multiple refineries and hundreds of oil wells spread throughout the residential areas, and it received a grade of D on these maps in 1939. And the appraisers noted that the whole district has been literally engulfed by oil wells, but also that the infiltration of supposed subversive elements is rapidly increasing, by which they meant immigrants and people of color. So they deem the area future residential desirability as non-existent. In contrast, if you look at this neighborhood here, El Segundo, it received a grade of C, despite the fact that it was literally a company town founded by Standard Oil. And the appraisers noted that there was the derogatory influence of oil wells, refineries, and tank farms, but that deed restrictions provide protection against racial hazards. So this neighborhood got a slightly better grade because of that. And today is predominantly white, 80% white, and relatively high income compared to the rest of the county. So with that background, let me tell you about these project goals of this project, which was led by my PhD student, Ali Barbarian. So we sought to identify water systems in Los Angeles that may be at risk of drinking water contamination because of oil and gas development. And two, to examine the contribution of historical redlining and present day racial residential segregation to the likelihood of oil-related drinking water contamination. So LA is kind of a unique context to ask these questions because of its history of oil development and the number of oil wells that are here in an urban area, which is very unusual. And also unique because LA has almost around 200 different water providers, which is pretty unusual. So most cities have one or two water providers, but due to the history of its development, all these little cities kind of growing together, LA has a large number of community water systems. So our first step was to identify which systems might be at risk. And we would consider them at risk if they had a drinking water supply well located within 1 kilometer of one or more oil and gas wells. So the 3 maps on the left show you the oil and gas wells we considered. So the pink ones are active extraction wells, which we considered them active if they had produced any oil or gas in the last 3 years. These well locations come from CalGEM, as well as the production data comes from CalGEM. In the middle, the yellow, those are extraction wells that haven't produced lately, so we consider those inactive, but studies have shown that many of them continue to leak air contaminants, and in many cases, really old wells were never properly plugged or decommissioned and can serve as conduits for contamination. And on the right, storage or disposal wells in green. And then the purple blob on the very right map shows you or illustrates how we made this designation of at risk. So this is the service area boundary. The purple area is a service area boundary for a drinking water system near Lancaster. You can see it's the wells, drinking water supply wells that it relies upon are in diamonds. And the blue ones are not within 1 kilometer of an oil and gas well, whereas the orange ones are within 1 kilometer of an oil and gas well. And so this system was designated as at risk. We then characterized the population served by each of these water systems. So we joined their service area boundaries to measures of present day demographics from the American Community Survey, the same ones I showed you before from the previous project. And historical redlining grades using these Hulk maps. So we determined the proportion of the surface area that was graded A, B, or C, or D, and the proportion that was ungraded. And then we derived a weighted redlining score that ranges from 0 to 100, with 100 meaning more of the service area received a poor grade. So this is just sort of a weighted average, and we weighted the poor grades more than the A grade. You can see the formula here. And so for example, in the little map here on the right, if this pink or purple area is a community water system, where 30% of its area fell within the blue polygon of a B graded area, and 50% fell into the C yellow graded Hulk map area, and 20% fell beyond any Holt grade, so it was ungraded, we would calculate its weighted score as 66. And finally, we also looked at present day segregation using the income of concentration at the extremes. This is an area-based measure of concentrated racialized economic segregation. So we assigned census tracts to community water systems if their centroid intersected with the water system service area boundary. And then ICE, this metric ICE ranges from -1 to 1, with the lowest values indicating a high concentration of marginalized populations, which we defined as people of color earning less than $25,000 a year. And values of 1 mean a high concentration of privilege. 100% of the population is non-Hispanic white people making over $100,000 a year. We categorized this variable into 4 quartiles to kind of mirror the 4 grades of the Holk maps, with quartile 1 representing the most marginalized, quartile 4 the most privileged. And then we also created this sort of weighted ICE score, again, ranging from 0 to 100, with higher scores indicating more of the tracts within a community water system boundary had a high concentration of privileged populations. Okay, and so here's what we found. A quarter, roughly, of LA County community water systems serving over 7 million people have a water supply well within a kilometer of an oil and gas well. And so the map on the left, any of the blue or purple water systems have at least 1 supply well near an oil and gas well. And the darker the shade, the more supply wells are near oil and gas. And we could see that at-risk systems had a higher average proportion of Latinx and Black residents and lower average percent white. They had at-risk systems had a higher percent of their service areas historically receiving a D grade on redlining maps and a lower mean percent graded A. And at-risk systems had a higher percent of their tracts in quartile 1 of ICE, meaning more of their population was living in these neighborhoods of concentrated racialized economic disadvantage. We also estimated prevalence ratios using a modified Poisson model. And these are prevalence ratios in 95% confidence intervals, similar to what I showed you before. So the predictor variables this time are scaled in units of standard deviation. So with this orange point that I've highlighted here, you would interpret as per standard deviation unit increase in the proportion of the population identifying as Latinx. We saw 2.8 times higher likelihood of the water system being considered at risk of oil and gas related contamination. Moving now to the redlining and segregation measures, we similarly saw that a higher likelihood of at-risk status per standard deviation unit increase in the proportion of the service area graded C or D. We combined those due to multicollinearity. We couldn't just look at D alone. The redlining score, was also associated with increased risk, as was the proportion of the present day population living in segregated census tracts and the continuous ICE segregation score that we calculated. Of course, the outcome here is just, proximity between drinking water supply wells and oil and gas. So we didn't actually look at any water quality monitoring results, or there really is no monitoring for many of the contaminants you might worry about coming from an oil and gas well. So there's not a lot of data there to look at. But we did make an attempt here, and I should say what I've shown you so far is forthcoming in the American Journal of Public Health, if you're interested. This here is preliminary and has not been submitted for publication yet. We've started looking at cumulative contaminant index, which is a measure we've used before. Basically, this work is led by Jenny Rempel at Berkeley. So she derived this CCI index across the 18 most ubiquitous chemical drinking water contaminants. And basically we sum the ratio of the max concentration observed in each system during the last compliance cycle divided by half its MCL. And we see some indication of an increase in the average cumulative contaminant index in systems that had a higher redlining score. These are the same metrics I showed you previously, percent graded C&D and the weighted redlining score. So for example, for every 10% increase in the weighted redlining score, we saw a 9% increase in the average cumulative contaminant index, but you can see these confidence intervals are pretty wide due to our low sample size. So in conclusion, I think this work helps show how racism continues to result in higher exposure to drinking water contamination threats, that statewide communities of color and domestic well communities face greater contamination. And in Los Angeles, historic redlining and present day segregation are related, correlated with oil and gas related drinking water threats. And, my hope is that these findings can help be used to target drinking water quality investigations in priority areas, inform efforts to develop groundwater management sustainability plans to protect drinking water resources for domestic well communities. And perhaps there's a lot of effort underway and recent ordinances that have been passed to retire oil wells in Los Angeles County and city. So, there may be opportunities to prioritize abandoned and retired wells for remediation if they may present a threat to drinking water. So I'll stop there. Very happy to answer questions. My email's here if any of this work interests you. We'd like to reach out, and all of the many great people who have worked on this are listed here along with our funding sources. Thank you.
I really appreciate all this information. It's really amazing.
Thanks everyone for tuning in.